Hello everyone, welcome to another session on statistics. So today we are going to continue where we had left off in the previous video. If you have not watched the previous video, please watch that video because this video is an extension of the previous video. So today we are going to solve few more problems, and we are also going to learn about t-test. So far we have worked only with z-test, so we'll solve t-test problems today. We'll also look at different variations of t-test: one sample t-test, two sample t-test, and paired t-test. So let's get started. So we had solved till problem number 4. So let's pick up problem number 5. So spend a couple of minutes in reading the problem. Let's understand what the problem is. So a chair manufacturer has spent 5 million in upgrading the equipments to lower the defects in chair. So right now, when the chairs are getting manufactured, we are finding defects in those chairs. The current defect rate is 20%. So out of 100 chairs being prepared, we are finding that 20 chairs are having some defects. So the chair manufacturer spent some money, around 5 million, and he upgraded the equipments to ensure that the defect rate drops. So you are asked to develop a hypothesis that the defect rate has dropped below 18%, or rather you are asked to test a hypothesis. So the owner believes that to test so the owner believes that his defect rate has dropped below 18%. So you are asked to test his hypothesis that it has dropped below 18%. So in order to work with it, in order to prove it, you pick up 150 random samples and found 30 defects. Now can you use this experiment to say that the defect has lowered, or rather the defect has dropped below 18%? I think that will be the right question. Okay, so let's get started with our tried tested formulas. So first what we'll do is we'll write the population data. So we'll take mu. So mu here is, just pause the video and tell me what is mu here. On a count of 5, 4, 3, 2, 1. The correct answer is 18%. If you have thought 20%, then this 21% has been given just to confuse you. It has no relevance in the test. We really do not care about this entire statement. Our problem actually starts from here, from this part. Okay. So now we assume that mean is 18% or 0.18. Let's calculate the standard deviation. Here, by the way, this is let mu be 18%, right? We do not know whether it is or not. So as far as the standard deviation is concerned, into 1 minus 0.18, so that gives me 0.38. So now we have got the mean and we have got the sigma. From the sample side, let's see what we have got. We have n, which is 150, and we found 30 defects. Now this mu is nothing but my defect rate. So x, or the value against which I am going to test, this should also be a defect rate. So how do I calculate the defect rate? I pick up 30 defects. We got 30 defects in 150 random samples. Okay. So 30 defects out of 150 random samples. We'll just come here in a moment. Now let's construct the null and the alternate hypothesis. So the alternate hypothesis is so we need to test this. So this is my alternate hypothesis, that mu is below 18%. Mu is less than 0.18. And my null hypothesis is that mu is 18%, right? So let's calculate the defect rate, which will be 0.2, right? So if we get 0.2. Now let's calculate the z-score. So z-score of x is equal to x minus mu by sigma x bar. So we also need to calculate the sigma x bar. So sigma x bar is sigma by square root of n, which is equals to 0.38 by square root of 150, which is equal to so 150 square root is 12.24, 0.38 divided by 12.24 is 0.03. So my critical value, sorry, my z-score is of 0.2 is x minus mu divided by 0.03. So if I calculate 0.2 minus 0.18 divided by 0.03, which is 0.67. So we got a z-score of 0.67. Now from here I have to find the p-value. So p-value is the probability that this particular statement is true. So let's find the p-value from the Z table. So this is the Z table. So our p-value is 0.67. So 0.67 is here. Okay. So 0.67 is 7.7486. Okay. So if this is my distribution, this is 0.18. This is 0.2. So my rejection region is here. So what I have got is a p-value of 0.7486, which means this side is 0.7486. I need this side. So this side is 1 minus 0.7486, which is 1425. Or in another term, so this is 0.2514, which means the probability of this statement being true is around 25.14%. Now if that is the case, I cannot reject the null hypothesis. I cannot, right? This statement can certainly be true, right? I cannot reject this. So if I look at carefully into this problem, why I got such a big p-value? It must have struck you that this time the p-value is really high. Ideally we want this p-value to be how much? To be less than 0.05. Then only I can reject the null hypothesis. But this time it's very high. How come this happened? And under what scenario this can happen? So if you carefully observe, when we had formed the null and the alternate hypothesis, here when we had done the experiment, we had found that the defect rate is 20%. However, when we formed the alternate hypothesis, we said that this is less than 18%. So that itself shows that my formulation of the hypothesis is not correct. Here I saw that it's 20%, but my hypothesis says that it's less than 18%. So these two are in stark contrast of each other. And it was expected that something like this can happen. The p-value got very, very high. So which means whenever you're constructing the null and the alternate hypothesis, you should first observe what you are trying to formulate, and you should observe the experiment properly, right? So let's get back to the previous problems once. Like in this problem, my observation is that 68% now is using tablet out of 200 random households, and previously it was 60%. So it's evident that it has increased. And if I put a alternate hypothesis that mu is greater than 60%, I'll be fine, right? But in this case, I clearly see that this is 0.2, but I found a hypothesis that it is less than 0.18, which is difficult to be true in any case. So in this case, my outcome is that I do not have enough evidence to reject the null hypothesis, or I do not have enough evidence against the null hypothesis. You can use any one of these statements, because the chances of the null hypothesis being true in this case is 25.14%. I hope this makes sense. So now let's move on to the next problem. So far, whatever we have seen, that all the problems we have solved are part of one-tailed test. Now, what does that mean? So if you look at our alternate hypothesis, so we had said mu less than 60%, right? Or mu greater than 110. So we have tried to solve this kind of problems. Where in the alternate hypothesis, if you see that I am checking only one side, that is either greater or lesser. This is called one-tailed test, when I am checking only one side of the distribution, which can be either greater or lesser. Now, if we want to test whether something is equal or unequal, that's where we use a two-tailed test. Why it's called two-tailed? Because not equal to means it can be greater or can be lesser. So let's write down. So if you see, it is not equal to, which means it can be greater or lesser both. It can be greater than 60 or it can be lesser than 60. Unequal means that. So here it is testing both the sides. So that's why it's called two-tailed tests. Are things going to change fundamentally? Not much, apart from one minute change. So let's take a look. So let's take this problem. So you have made a new recipe in your restaurant. Okay, so you're a cook maybe, and you constantly innovate. So as part of your innovation, you have made a new recipe, and previously in your restaurant you used to have a footfall of around 60 customers on an average per day. On an average per day, I would say, with a standard deviation of 10 customers. So after you have made the recipe, you counted the number of customers over the last 5 days, and you found around 400 customers over the last 5 days, which means an average footfall of 80. So has this recipe worked magic? So if I have to convert this in a two-tailed test, ideally, from this question I would say, okay, if it is greater or lesser, but let's convert this into a two-tailed test, right? Or so has this recipe worked magic or has it bombed? So basically we are trying to see if there has been any change after you have introduced this new recipe. So what we'll do is, let's write down the problem. So the problem is, you have a footfall of 10 customers on an average per day with a standard deviation of 10. Okay. So population data, that is the first thing you should write. Mu is equal to 60 and standard deviation is equal to 10. That is my population data before we introduce the recipe. Now from the sample perspective, you have X and you have N. So X is 80. Last 5 days, number of customers is 80. And N is 5. So let's write down the alternate and the null hypothesis. Let's go to the problem. So the hypothesis which we are testing is whether it has changed from 60 customers or not. So not equal to 60. Always remember, alternate hypothesis has to always deal with a change. So whenever you notice some changes, then only you want to do this hypothesis testing. And whenever you have noticed a change but you just want to confirm that statistically, that's where you end up doing hypothesis testing. So alternate hypothesis is what your belief which represents a change, and null hypothesis is something which represents a kind of a equilibrium. That means nothing has changed. So let's do the calculation. So first we'll calculate sigma x bar. which is sigma divided by square root of n. So sigma is 10 by square root of n, which is 5. So 2.23 10 divided by 2.23 is 4.48. This is my standard deviation. So z of x is 80 minus 60 divided by 4.48. So 20 divided by 4.48 is 4.46. It's too high. I don't even need to look at anything. I don't even need to look at the p-value. A z-score of anything, if it crosses 1.6, 1.7, it's like too high. So I can confidently, and in this case what will happen is that the p-value will be too low. So if the p-value is too low, the chances of this statement occurring is going to be very, very low, which means I can reject this and I can accept the alternate hypothesis. Now let's try to make some changes to this and see how it works intuitively. Now if you think this is 80 and here like it's 60 was the previous footfall with a standard deviation of 10, and here we found 80. So what we can clearly say is that it's very obvious that something has really changed. The number, if you see the number intuitively also, it looks to be changed. Now let's take an exercise. What we'll try to do is, let's try to see how we can increase the p-value here. Which means if I have to increase the p-value, I have to decrease this z-score. Right? If I have to decrease the z-score, what are the ways in which I can decrease? One way is I can increase this. If standard deviation goes high, then automatically z-score will decrease. So let's come here. If I have to increase the standard deviation, what I can do is I have to decrease this n. If I decrease this, then standard deviation will go high. That's one way. Another way is if I increase this standard deviation, then also sigma x bar will be higher. So for example, let's say make it 20. If this is the case, then what will happen? So 20 divided by 2.23, which is square root of 5, is 8.96. Will it make a difference? So 20 divided by 8.96, it will still be, if this part is 8.96, so 20 divided by 8.96 will be 2 point something. No, still high. So still I am not convinced. So let me make it even higher. Say 30. Let's see now. Does that make a difference now? So 30 divided by square root of 5. Let's try this one. 13.45. Yeah, now I think we should get something meaningful. So this part will be 13.45, which means so 20 divided by 13.45. That is 1.48. So if that is the case, let's see. So Z score is 1.48. Okay. So now the p-value does not, I don't think it will be too low. So 1.48. So let's first draw the diagram. So this is my mu, which is 60. This is 80. And this part is my rejection region. So if I go and find out 1.48, so 1.48 is 0.93, which is this side. So if I have to calculate the other side, this is 1.1 minus, 0.93, which means 0.07. That's my p-value. Now, for a two-tailed test, so far what we have seen is that for one-tailed test, the p-value has to be less than 0.05. In this case, this is slightly higher. So anyways, I cannot reject the null hypothesis. But for a two-tailed test, this is a change. It is not 0.05 anymore. Because now I am testing two sides, greater as well as lesser, which represents inequality. Right? So these 0.05, which I was getting for one-tailed, where I was only testing either greater or lesser. Now this 0.05 is going to be get divided by 2, because this will, both of them will take or stake claim in this 0.05. Previously it was only being taken by greater or lesser. So here this is not equal, which means both greater and lesser, and both of them will take a pi on this 0.05. If that happens, then what will happen is for each of them, like this one is 0.05, fine, no problem. Both of them combined is 0.05. but each of them will get 0.025. Which means when I'm getting the rejection region, I'm only getting it from one side. So whatever we are getting from 0.07, this is not sufficient for this. It's only testing greater side. But I also need to check the other side. So in this case, my p-value will be this into 2, which means it will be 0.14. So we can clearly see that I cannot reject the null hypothesis here. So let's make some quick changes. So let's bring down the sigma, maybe make it 25, just to now check if I want to now reduce the p-value slightly, and I want to reject the null hypothesis. So if this is 25, so 25 divided by 2.23 is 11.2. Twenty divided by 11.2 is 1.78. So if that is the case, let's find out the p-value. So 1.78, p-value is 0.9625. So let's write down 9625. So 1 minus so 3.75 is this one. So in this case, 0.03.75 into 2 will be my p-value. So no, it's still we are not able to reject. So what I have to do is I have to reduce this slightly more. So if I say make it 22, I think we should be able to do that trick. So 22 divided by 2.23 is 9.86. So this is now 9.86. So 20 divided by 9.86 is 2.02. So our Z score is 2.02. So 2.02 is 0.9783, now I can clearly say that yes, we can reject it. Why? Because now if you look at carefully, whenever I'm calculating one side, right, I want one side to be actually less than 0.25, right? Then only if what is my ultimate objective? My ultimate objective is to get a p-value of 0.05 for both greater and lesser, which means each side is getting 0.25, sorry, 0.025 actually. So each side is getting 0.025, which means this is my cutoff, because this side is 0.97. If I have to get a p-value of 0.025, then I have to cut at this point, which means 1.96 is my cutoff. If my z-score goes beyond 1.96, then I can reject the null hypothesis. So for a two-tailed test, the shortcut is a z-score if the z-score is between this range, then you can not reject H0 or null hypothesis. Okay, and if the z-score is greater than 1.96 or lesser than minus 1.96, then you can reject the null hypothesis. So now let's quickly do one more problem, our last problem in z-test, just to recap our concepts. After this, we'll move on to t-test. So your restaurant has got red interiors and the customers were spending before 5,700 with a standard deviation of 3,000. Fair enough. Now you have changed the color. So from red, probably maybe you have done green or blue, whatever. Now you believe that the customer spend will also vary with it. So you randomly surveyed the spend by 300 customers and you found that their average spend is 6,000 rupees. So now the question which we need to answer is, did this change of interiors or did this change of colors, did it have any impact, rather any significant impact in spending by the customer? So let's write down the problem from our population. We have mu, which is 5,700. We have sigma, which is equal to 3,000. And here we have sample. So I have x, I have n. So this is 300 and my x is 6,000. Now let's write down the null and the alternate hypothesis. So the null hypothesis is that mu not equal to 6,000, sorry, not equal to 5,700. And here mu is equal to 5,700. Now let's calculate sigma x bar. Sigma x bar is sigma by square root of n, which is 3,000 by square root of 300. This is 17.32. So 3,000 divided by 17.32 is 173.21. Now let's calculate the zx, which in this case is x minus mu by sigma x bar, which is equal to 6,000 minus 5,700 divided by 173.21. So we get a z-score of 1.73. So if we see here, it is falling in between, which means I cannot reject the null hypothesis. I'll say, sorry, I do not have enough evidence to say that the spending has changed. So I cannot reject this. Now, if I have to increase the z-score, here notice that I have not even looked at the p-value. In case I have to, let's do that as well. So this is 5,700. This is 6,000. And this is one of the rejection regions. The other is on this side, but I'll not calculate there. I'll rather find it here and then multiply it. So z-score of 1.73 is 0.9582. There is the other side. This side is 0.9582. So this side will be 1 minus 0.9582, which is equal to 0. So my p-value is 0418 into 2, which is 3608, which means the chances of this being true is 8.36%. So that's why I cannot reject the null hypothesis, because this has to be less than 5% for me to reject it. So let's try to just make some changes and try to see if I can make it reject. At what value? So ideally this has to be greater than 1.96. So if I have to increase the z-score, I can probably increase this value by a bit. See if I make this 6,500. So in that case, this will be 6,500. So 500 by 1.73. So 500 divided by 173.21 is 2.88. A z-score of 2.88. If I come here, 2.88 should be this one, I guess. Yes, 0.9999.8. Okay, so this is if that is the case, then this is 200, which means even if I multiply it by 2, it's not going to be very high. So in that case, I can reject. So this is it from z-test. Now we'll continue with or start t-test. Okay, so now let's start exploring t-test. So let's look at t-test. So t-test is a mini version of z-test. It works like z-test, but with some differences. So all the conditions which we have done so far, which we have satisfied so far, the concept of null hypothesis, alternate hypothesis, concept of z-score, concept of central limit theorem, to a very large extent they apply to t-test as well. Of course, there are some tweaks. So as I said, t-test is a mini version of z-test. So when do we use t-test? So we use t-test when, number one, normal distribution, the underlying distribution is normal. In one of the later lecture series, I will give you a brief overview on what test to use when and what are the conditions. So just now know that t-test works with normal distribution. The same is also applicable for z-test, by the way. So both z-test and t-test work on normal distribution. Here the metric in consideration is mean. So metric in consideration, so we'll be working with mean. There are some non-parametric tests where we will consider median, which will, as I said, show in the later videos. So here metric in consideration is mean. In t-test we do when generally the number of samples is less than 30, and number 4, when the population standard deviation is unknown. Is not known, right? However, rest of the concepts are more or less the same. Here also we'll try to calculate something called a T-statistics, the way we were calculating the Z-score, and then we will be looking at the p-value, though in a different way. We'll be looking at a critical value, and we'll be comparing the calculated value and the critical value, and then we'll make decisions whether we should accept or reject the null hypothesis. So let's look at a problem. Okay, before that, let me also mention the varieties of T-test available. So the main varieties of T-test are one sample T-test, two sample T-test, pair T-test. So let's look at each of these problem one by one. So let's read problem number 8. So let's read the problem first. So it is recommended to walk 10,000 steps per day to be healthy. So when you walk more, you reduce obesity, and that's good for health. And the doctors have prescribed to walk 10,000 steps per day. And these days, as you know, there are a lot of apps, wearables through which you can track how many number of steps are you taking per day. So you randomly surveyed 10 people and found that they are taking these many number of steps respectively. So when we look at this particular data, it's like very evident that these people are taking less than 10,000 steps, most of them. Yes, there are some exceptions, but most of them are taking less than 10,000 steps. But can you use this data to infer about the entire population? Can you use the samples which you have taken for 10 people to infer about the entire population and say that the entire population is taking less than 10,000 steps? That is the problem. So here, first things first. So this is a one sample T-test, because what we want to test is if the sample mean, which means sample mean is coming from here. These are the samples which we have taken. If this mean is statistically different from a hypothesized mean. Here, this is not an exact mean. This is not my population mean. This is the hypothesized population mean, right? This is not the exact mean. I do not know, right? How many steps people are taking. We have hypothesized that people are taking these many number of steps, and we want to compare the mean of this group, the mean of samples, versus this hypothesized mean. So this is my hypothesized mean. So looking at these two numbers, can I say that this mean of samples, whatever we are getting, right? And here, mind it, we have worked with only 10 people. And looking at this, can we infer the same about everyone in the population? That's the problem. So let's try to solve it. But before we try to solve it, one question which might be striking you, that it's actually looks very simple, which means if I have to do a survey, I just need 10 people, which means I can talk to my father, I can talk to my mother, I can talk to my sister, I can talk to a couple of friends, couple of colleagues, couple of neighbors. I can collect that data and then infer the same about the entire population. It's actually simple. Why does statisticians take so much of pain in gathering so much of data? It's just 10 people whom we need to talk, and we know more than 10 people, right? That might be coming in your mind. Now, one thing which you need to remember is that these 10 people are randomly surveyed 10 people, which means that it cannot be biased. You cannot say, okay, I am going to pick this person, this person, this person. I know that they are taking 10,000 steps or less than 10,000 steps. I speak to them, I form my hypothesis, I do the testing, and I can give a result. No, because they are not randomly surveyed. You know about them and you are picking up their information. That's not random survey. Random survey means you do not know about that person. Suppose you go stand in front of the road, you just randomly ask people. And that also cannot be from a particular state only or a particular city only. Then you will lose diversification. So it looks very simple that I just talk to 10 people and my work is done. That is not the case. Okay. So now let's try to solve this problem. Let's first see what information do we have in our hand, and then let's try to solve it. So the first information which we have in our hand is a hypothesized population mean. So just for simplification, I say this is my population data. No, this is a hypothesized mean. This is not the real mean. So this is 10,000. So now we'll find sigma. So we come to the problem. We are trying to find a hypothesized sigma, but hold on. This is hypothesized mean. This is not my population data. And in this case, I don't have a standard deviation. And if you remember, I use t-test when my standard deviation of the population is not known. Fair enough. So I do not know this. Let me just put a cross. This is not x, this is a cross. Next thing what we'll do is we'll form a alternate hypothesis and a null hypothesis. So my null hypothesis is that it's less than 10,000. My alternate hypothesis is that it is equal to 10,000. Now, I do not know the standard deviation. So, this is my sample site. So, let's write down whatever we have. So, we have a mu bar. Which is equal to mu, which is equal to 10,000. Then sigma x bar is equal to sigma by square root of n. But unfortunately, in this case, we cannot do this because there is no sigma. I do not know the sigma. Okay, fair enough. Let's look at n, which is equals to 10. And we also need a critical value, which we can call as x. Which is also something which we do not have. So let's try to figure these things out one by one. So let's test. So here I have pasted all these numbers. So all the numbers I have copy pasted, and then I am calculating the mean and the standard deviation. As you can see, the mean is 8595 and the standard deviation is 1428.36. So here from the sample I can calculate the standard deviation. I do not need the population standard deviation. So it's possible for me to calculate the standard deviation. So my standard deviation is 1428.36. And the mean is 8595, which is nothing but this x. So if you remember during z-test, right? If you remember during z-test, this used to be our x, the average in the in the sample side. Here also used to compare it against this average in the sample side. Here we do not have it directly, but we can certainly calculate it from here. So we have the standard deviation and the mean. Either they will be mentioned explicitly, or you can be given data like this and you can calculate the mean and the standard deviation. Now for t-test, we will calculate something called a t-statistic. So the funda is the same, x minus mu bar divided by standard deviation by degrees of freedom. I'll just explain you in a moment what is degrees of freedom, and you get a square root here. Okay, so we'll just pause here and let's just quickly understand what is degrees of freedom. Again, a common mistake which I see between people is they say degrees of freedom is n-1, where n is the number of samples or the population size. That is not correct. In most of the scenarios, it is n-1, but let's understand the concept. Suppose I have 4 numbers. Suppose they are 4, 4, 3 and question mark. Now what I tell you is, I tell you that their average is say 5. Now looking at these details, can you calculate this particular missing number? The answer is yes, we can, and the answer will be 9. So as you can see, knowledge about these 3 numbers was enough for me to derive the 4th number, as long as I know the average or some metric. Average actually works in most of the scenarios. So in this case, out of 4, knowledge about 3 variables or 3 observations is good enough for me. So in this case, my degrees of freedom is n-1. For this particular data, it's n-1, where n is the total number of samples. However, is it always n-1? Let's take a scenario. Suppose I say I have 4 numbers, 4, 4, question mark, and I tell you that the average is 5, and I also tell you that suppose this is 1, 2, 3, 4. I also tell you that number 3 is equal to number 4. If I tell you these 2 things, can you calculate these 2 numbers? The answer is yes, we can. And in this case, the answers are 6, 6. Looking at these 2 scenarios, right? The answer is 6, 6. So here in this case, as you can see, the degrees of freedom is n-2. So not necessarily that it has to be n-1. That's the message which you need to take over or take home. Most of the scenarios it will be n-1, but not necessary. Here it's n-2 because knowledge of n-2 variables was good enough for me to derive the next numbers when I know this particular condition. Okay, so now we understand all of these things. Let's just plug the numbers. So x is 8595 minus mu is 10,000 divided by 1428.36, which is my standard deviation, divided by degrees of freedom, square root of degrees of freedom, which means here my n is 10, so 10 minus 1, and that comes to, so let's first calculate the denominator. 1428.36 divided by 3 is 476.12. So this is the denominator, 476.12. Now let's come to the numerator. 8595 minus 10,000 is minus 1405. That divided by 476.1, and we get minus 2.95. So this is my T statistic, and we'll going forward we'll call it as T calculated. You can call it as T calculated. Also, you can call it as T statistic. It's very similar to our Z-score. Now, let's find out something called a critical value. So here we have the T table. Now, since this is a one-tailed test, here as you can see, this side is the degrees of freedom. So let's look at the critical value for a one-tailed test. So here my degrees of freedom is 9. So I'll come here, and this is the critical value for degrees of freedom is equal to 9 for a one-tailed test with the significance level of 0.05. So this is my critical value for degrees of freedom 9, significance level 0.05, being it a one-tailed test. So let's note down this value, 1.833. Okay. So my T calculated, we had found it to be minus 2.9, and T critical is 1.833. So if we just draw the curve, suppose this is my mean, and this is my threshold, which is, since here the way the T table is constructed, it does not take care of the negative values. So whenever we get a positive value, in case we have to work with a negative value, in case here since T calculated is negative, what we'll do is we'll put a negative value here. So this part is my, or this point is my T crit. Now the significance of T crit is that T calculated should be between mu and T crit. T crit is the maximum point beyond which I'll reject the null hypothesis. So here, if my T calculated is here, anywhere here, between here and here, if I can find a T calculated say here, then I cannot reject the null hypothesis. If it goes on this side, then I can reject the null hypothesis. This is my cutoff. The moment it crosses this cutoff, you can reject the null hypothesis. So that is the significance of the critical value. It's a cutoff, it's a threshold. So in our case, let's see where we find our value. So this is our T calculated. So as you can see, T calculated is beyond T critical. So in this case, the thumb rule which we will follow is, if T calculated is less than T critical, then reject H0. So in my case, H1 was that mu is less than 10,000 and H0 that H0 is mu is equal to 10,000. So in this case, I can comfortably reject the null hypothesis and I can accept the alternate hypothesis. So here I reject the null hypothesis that people are walking 10,000 steps. That hypothesis is rejected, and the hypothesis that people are walking less than 10,000 steps, that particular hypothesis is accepted. So here my hypothesized mean is this, and as you have seen here, so we see that yes, the sample mean which we calculated from here is statistically different from my hypothesized mean. Okay, in this case it's less because it's very, very evident that they are taking less than 10,000 steps. Now we'll look at a two sample t-test. So this test is significant when we are trying to test the difference between two population means. So let's read the problem. So we have visited two schools. In school A, we randomly surveyed around 30 kids and found that their average IQ is 110 with a standard deviation of 5. In school B, we randomly surveyed 20 kids and found that their average IQ is 115 with a standard deviation of 10. So now we can test the hypothesis that the IQ between the kids in the two schools are not equal. So I have, as we can see here, we test the difference between two population means. So here my two populations are school A and school B. And in school A, I have randomly surveyed 30 kids and I have noted down their average IQ and the standard deviation. I have done the same in school B, where I have randomly surveyed 20 kids and noted their average IQ along with the standard deviation. Now I have to test the hypothesis. The IQ between the kids in the two schools are not equal. So in this case, let's do a two sample t-test. So as you can see here, my null hypothesis is that mu A equals to mu B. Mu A is for school A or group A. Here as you can see, we have two schools. H1 is that the mean are not equal. Now how do I calculate the T statistics or the T calculated? The formula is this. So we take the mean of group A, in this case which is school A. We take the mean of B, in this case which is school B. We take the standard deviation, and then we have the number of observations with which we are dealing. So let's just plug it and see what we have. So in school A, we spoke to 30 kids. In school B, we spoke to 20 kids. In school A, the average is 110 with a standard deviation of 5. In school B, it is 115 with a standard deviation of 10. So now let's calculate this step by step. First, I have calculated the numerator, which is mu A minus mu B. So 110 minus 115, that is 5 or minus 5. Then denominator 1 is nothing but this part. This is deno 1. This is deno 2. Then I'll add them, and then I take the square root. So I've done it step by step. So we have calculated numerator. This is the numerator. So denominator 1 is 0.83 sigma square divided by n1. So sigma square, as you can see, I have taken standard deviation square, which is B4, and divided by B2, which is nothing but n1. Similarly, denominator 2, C4 is nothing but my standard deviation square divided by C2, which is the total number of kids we have surveyed. Then I have added these two, which is this part, this addition. And I have taken the square root, and then I have calculated T statistics, which is nothing but numerator divided by the denominator, and we find that T statistics of minus 2.07. So this is my calculated value. Now what is my critical value? If I do a say a two-tailed test, then my critical value will be this. Two-tailed test with 0.5 as my p-value, or 95% confidence, whatever you want to say. Here let's see how many records we have actually. So here we are dealing with, here for my bigger case it is n is equal to 30, and here it's n is equal to 20. So in this case both are different. So let's pick n is equal to 20. So here, if I look at it, the p-value or the critical value is 2.086 if I pick n is equal to 20. Okay, so this is 2.086, this value for n is equal to 20, critical value of 0.05, and I am doing a two-tail test. So let's take this value. So my critical value is 2.08, and I will put a negative sign, and as we can see that it's like very close, and the t statistics is inside is less than the t critical value. So if I had to draw a graph, if this is my mu and this is my t critical and this is where my t calculated is, very close, it's like neck to neck. So in this case I do not have enough evidence to reject the null hypothesis. In this case I cannot reject the null hypothesis. I hope this is clear. So now we'll move to the last test as far as t-test is concerned, and that is a paired t-test. So we use this test when we are interested in the difference between two variables for the same subject separated by time. Suppose you have studied the score of few students, or say in this case one student, I would say score of a student. Pre and post joining a course. Assuming that here the data is normal and here also the data is normal, both pre-course and post-course. The question is, do you observe any statistical difference between the scores of the student after joining the course? Which means, did joining the course help the student or not? So here we are looking at the same subject. The same subject is the student, separated by time, pre-course and post-course, and we are interested in the difference between the two variables. So let's put these values in Excel. So here I have put these values in Excel, and the way to calculate the t-test is, first we'll calculate the difference, which is this part. We'll calculate the difference square, which we require here, and then the rest is straightforward. So here what we have done is numerator minus 33, which is nothing but difference. Then denominator 1 is 2457. Let's see what do we have for denominator 1. So denominator 1 is nothing but n, which is this. It is nothing but the count multiplied by summation of d square. So here what we'll do is, so multiplied by summation of d square, which we have got from here, the difference square, minus summation of d square, which is this part. So I take the summation of difference, which is something which I've got here. Then I want to subtract this minus this, so denominator 1 minus denominator 2, and I get this value. Now denominator 3 is this entire expression, the numerator versus the denominator. The numerator in this case is this value. This is my numerator, and this part is my denominator. And then finally I take the square root. After that I calculate the t-statistics divided by numerator and denominator. So that gives me my t-statistic. And here for degrees of freedom 9, we have already seen that the value is 1.833 for one tail test. For two tail test, let's figure out what is the value. This is the value, for 0.05, 2.26, and the value which we have got is 2.52, so slightly off, which means I can reject the alternate hypothesis, reject the null hypothesis and accept the alternate hypothesis. So that's about paired t-test, where we are pairing for a same subject attributes which are separated over time, pre-test and post-test. The substitute of this test, this paired t-test, we are assuming that this distribution is normal. If this is not normal, then the substitute of this test we'll learn in the later videos. We have something called a Wilcoxon test. So we'll learn about it in the next video. So I hope you have been able to grasp Z-test, T-test, hypothesis testing, the formulas, and we have solved 10 problems. So if you like the videos, please like, comment, share, subscribe. If you want to enroll in the course, please click on the link below. So I will be back with a new video where I will be discussing few other tests very soon. Till then, happy learning.